Good afternoon, morning, evening, wherever you are. And thanks for taking the time to join us. As Jennifer said, today I'll be looking at residual oil saturation. I'll look at these four main aspects. What's so important about residual oil anyway? The problem and the uncertainty in residual oil, and what I'll look to do is try and disambiguate some of the understanding and some of the uncertainties in what we're talking about. I'll look at some of the factors that affect residual oil saturation, some of the laboratory factors affecting laboratory measurements, and then ultimately look at, is there a solution? Is there something that we can do, and what's the best method to attempt to obtain residual oil saturation, true residual oil saturation? So looking at this, what's so important? Well, I think first we need to give some definitions of what we're talking about, or what I'm talking about when I talk about residual oil saturation and true residual oil saturation. So remaining oil saturation is what I would term as a saturation after a limited amount of injection. And that would be generally true of say, field injection times, field injection processes, that we have a limited volume of injection, and with different reservoir layers and compartmentalization, different regions, different aerial flow, sweep efficiencies, then we could observe different pore volumes of throughput in different areas. But overall, the reservoir sees a fairly limited injection volume. And although the terms remaining and residual basically mean the same thing, when we refer to remaining oil saturation, it means that we've come to some limited part. There's some oil remaining, but that oil can be produced. When I talk about residual oil saturation, it's usually a laboratory term of this is the maximum throughput, or the minimum residual remaining after, say, tens or hundreds of pore volumes of injection. Now, that's not going to happen in the field, but it's also subject to certain artifacts of the laboratory process. So it also may not be true residual oil saturation, and there still may be additional oil that might be produced. And so true residual oil is that the real residual that we're injecting for longer or injecting under different pressures is not going to have any effect. The only way of reducing further residual oil saturation in this true residual oil would be to use some form of EOR and alter interfacial tensions, etc. So that's what I'm terming these things. And one way, these are some nice pictures of pore casts. So I think it was in the 50s, 60s, 70s, some pore casts were used using things like wood metal to look at and visualize oil saturation. And these would be remaining oil saturation. So with remaining oil saturation, what we can see here is the oil is still connected with additional oil. So through, say, a pore throat here into a pore space, and several pores of oil are still remaining there. And because these are interconnected, and there's a potential this whole portion might be connected with other pores off the picture here. Because they're still interconnected, they still may be produced. Whilst in this term, when we start to see globular forms of oil, then this is probably never going to be produced. And that would be more like true residual oil. This is a pore cast of one droplet that has just been caught, maybe just at the point of its snapping off, and about to be true residual, but at this stage here was just beginning to push through, potentially push through a pore throat. So over the years, I've had lots of comments like, and this is partly the reason why we called this needless or required, because I had lots of comments over the years from reservoir engineers and asking or stating things like, well, laboratory measurements, they overestimate the reservoir potential. They're not realistic. And that's correct in some ways. For the little core that we're using in the laboratory, it's not going to be the same as the reservoir. We are inputting hundreds of pore volumes of injection rather than limited injection. Or my reservoir will never achieve this low SOR attained in the lab, so why bother? And I can see that in some ways I can see the point, because it's potentially expensive and it's quite often quite difficult to get the budget. For some reason, we're okay with putting budgets into exploration, but when we come to try and test and understand our reservoir, for some reason it becomes more problematic to get budgets to then get a better understanding of how best to handle our reservoir and how best to produce. However, there will be some regions of the reservoir, so certain compartments, certain layers that will observe significant volumes of injection. And I've got a little cartoon here to show that, so that throughput is a function of distance from the injector. So that as we inject through the sample, as we get to this end, as the water begins to approach the producer, then regions of the reservoir close to the injector have not observed one pore volume of injection. So at the point where one pore volume has been injected into this system, then at halfway, basically we've got two pore volumes will have been injected at halfway, and at a quarter of the way, roughly 4 pore volumes, and so on. So as we get closer and closer to the injector, larger and larger volumes have been put through that rock in this region. So we could have tens, potentially hundreds of pore volumes in portions of this. If we take that, so the throughput is a function of distance, and the closer to the injector, the larger the throughput. If we take that one step further and take those, the different layers that we can see here, and maybe consider these as different permeability layers. So if we looked at the height and its relative permeability, we'll say this is 0.5 of all of the permeability, the total permeability. This first layer is 0.1. Then as we inject, what we get is segregation of flow, and we'll have most of our flow through this top layer. And as we get breakthrough through this thief zone or high permeable layer, we get one pore volume, but this layer has not seen one pore volume. It's probably seen overall about half a pore volume, but the layer here has not seen any injection. So you begin to get differences of flow. And if we take that again to, if we consider then this second layer, and as this second layer begins to break through, what's been happening is this top layer has continued to flow. And so now we have a situation where our pore volume in this second most permeable layer has achieved one pore volume, at least at the outlet, but this top layer has actually now seen 2 pore volumes of injection at the outlet, and so on. And at this around about 5 meters in, it's actually seen 80 pore volumes of injection. So there will be, and this is for a 200 meter distance between injector and producer. So there will be areas of your reservoir that have significantly higher throughput than what the overall reservoir has observed. And if we're underestimating residual oil in those sections, then it's going to have a large impact on, or a potential impact on our production models and what we're simulating in production. So correct evaluation of SOR is vital for understanding that's the overall secondary or tertiary production. If our residuals from the laboratory are saying what is going to be 30, then that's a completely different story than if our residuals were saying it's actually more towards 10. Certain portions of your reservoir will achieve 10% residual. So that's a significant additional potential volume. And that's going to impact not just secondary, but particularly EOR, where you may be having to put more investment into an EOR process. You want to understand what additional advantage is going to come from that enhanced oil process. And also one of the things that I've observed over time is that if SOR is wrong, then many of the data that is working towards that, so things like relative permeability curves or capillary pressure curves, may also be incorrect as it moves towards that. And one example here is that if we apply different forces in a centrifuge test, so these are data from centrifuge analyses. These are relative permeability to oil. So saturation on the bottom curve, sorry, the axes haven't been labeled, but this is saturation, water saturation on the bottom, relative permeability on the y-axis. So my relative permeability to oil under a high force, which has achieved residual saturation, I get this kind of curve. But if I were to perform that at a slightly lower force that didn't quite achieve residual oil saturation, it's not that it follows the blue curve and then just cuts out towards SOR near the end. It's actually the whole curve has been impacted. And so by not incorrectly understanding SOR, we may also be suppressing relative permeability. That will ultimately impact our fractional flow curves, and that's going to impact all of our simulated data. Excuse me. So what is the problem? Where is the uncertainty, and what is its potential impact? Well, one of the issues is that the laboratory testing itself, the data itself, can be incorrect. So this is some data. It's a fairly well-known graph of wettability versus residual oil, where we're going from water wet here and a high residual oil saturation. It then reduces as we get to mixed wet conditions, and then increases again as we get to more oil wet nature. And so this is used to show that mixed wet can get to lower residuals, but actually really this curve is probably something more like this. And this data here is probably a function of core flooding processes where the artifacts, boundary conditions of the laboratory test have not been taken into account. So these are impacted by capillary pressure interfering with the relative permeability core flood. and really should be down here, but it requires much larger forces and much longer throughput times to achieve the residuals in here. So effectively, this is possibly what is happening anyway. However, in the field, we won't have the same boundary effects. the boundary effects in the field that we observe in the lab are close to zero. So some of the other potentials, this is a field that we studied where there are more than 200 data points here of residual oil saturation plotted against the initial relative permeability to oil and based on water permeability. And there's a massive variance here. So, you know, what is the starting point of this curve, of these curves? How does this correlate to my reservoir properties to different layers? Well, one of the things that we can do is plot those data versus the absolute permeability. It didn't help. Look at other variances like considering the different fascies, maybe reservoir quality index or hydraulic units. So different petrophysical ways of determining the different rock types and fascies and lithologies, layers in my reservoir. And that still hasn't really significantly reduced some of the uncertainty in these residual oil saturations. So one of the things that we want to be able to do is consider why this might be. Are there ways that we can actually correlate residual oil saturation to some data? And much of this, I will have to say, was because of poor quality control on these particular tests. Poorly designed tests and poor quality control on those tests. This next slide is just showing you a case from Shell. This was published in SPE, this SPE number here, where the reservoir was about 12.2 million cubic meters. That's probably roughly about 50 million cubic barrels, 50 million barrels. What they did was, there was a study that had looked at residual oil saturation. It was done in the late, it was done pre-1998. I think it was done in the late 80s. I can't remember exactly, but it was all done water wet. And the residual oils on average were about 33%. Then a program was put in place to put actual wettability aging in place to get to correct initial saturation of the reservoir, age the samples and perform the tests again. And this time we got to 16%. So a much reduced saturation, and that's a 17% difference in residual oil saturation. There's also then another potential issue that we observe in the laboratory is truncated data. So particularly when we're doing core flooding. So that by core flooding, generally we're only able to get down to about 10 to the -3 in permeability. And sometimes that could be significantly a difference in the residual saturation at 10 to the -3 compared to what the real saturation is here. And we see a variance in these data of approximately ±8 saturation units, but going from 0.75 to about 0.9, with the average being here about 0.84, 0.85. But most of the core flood data was cutting off at 0.72, which is about 0.13 of a difference in saturation. So 13 saturation units difference. But what's the point of this? Well, if we take that, if we look at the green curve here, generally the data is sort of following the average here, but it's just cut off short. So surely we can just use that, that relative permeability in here up to that point. And many simulators have a cutoff of 10 to the -3 anyway in many tables, because that's often what's given in core flood data. But this is the impact that inputting truncated data is. So the dotted blue line is exactly the same relative permeability, just truncated off at a higher residual. And the impact of that when looking at cumulative production is this here. It's about 2.6 times 10 to the 5 cubic meters, whilst the additional production from this non-truncated is an additional probably 0.3 times 10 to the 5 cubic meters. So there's about 10 to 12% error by a truncated system. So it can have an impact on our simulated reservoir simulated production. And Jos Mas from Shell, he in some of his materials, he would reckon that generally or globally we're underestimating or overestimating residual oil by about 10 to 15%. So that's a significant impact. And just another one to show you the impact of using data that has been performed and hasn't considered all of the potential laboratory artifacts. These are relative permeability curves. They're the true curves in the lines here. The other data here in this turquoise, purple and gray, they are laboratory derived data that haven't taken into account capillary end effects or boundary effects. And the curves here, so this blue is the turquoise here. So at a low flow rate, this is the rel perm that would be derived from a plug. And so we get a low plateau, a short plateau, early plateau. With the purple data, which was done at a higher flow rate, we get a slightly later and a longer plateau of oil production, oil rate. And using the lines here, that's the green one in here with a slightly later plateau again and a longer plateau of production. So these have significant impact on your reservoir simulations, which is why it's important to understand where the true residuals are. So in some other cases, this is where we've got basically the same Corey function, just a difference in the residual oil of 5 saturation units. That results in about a 7% recovery factor difference. And for 30 million barrels of reservoir, that's about 2.1 million barrels uncertainty. That's approximately $130 million of uncertainty or missed oil because of an error in residual saturation. In another one where this has had this was the laboratory output without artifacts being accounted. This is it simulated with all artifacts accounted. That's a 19% recovery factor, which ultimately equates to $340 million of uncertainty of these two curves. So it can have a significant impact. So what factors affect the laboratory measurements? Well, these are wide and various. It starts from coring. And if you've attended any of our previous webinars, you'll have heard how I've gone through from coring, through core handling, through handling in the laboratory and the processes that we're using in the laboratory, quality control. All of these processes can have an impact on the residual oil saturation. So the cleaning process can. But I'll come back and look at these a little bit when we start saying, well, what is the solution? What should we be doing? But at the moment, I'll look at things like this, stabilization criteria and some of the experimental artifacts. So with stabilization criteria, this is a curve of capillary pressure. So this is a process of
approaching residual saturations. This first ones, the green triangles here are showing data where a limited time has been used, 8 hours for each step, and assuming that things are stable after a certain period of time. Whereas the blue lines here are showing the whole process being logged and waiting for stability at each stage, ensuring that we have stability. And the impact on the capillary pressure curve is this. So a capillary pressure curve derived from the triangles looks like this. The capillary pressure curve derived from the stable criteria looks much different. And all of the area in between is lost saturation because of the way a test has been performed. And this is either in this drainage process or in imbibition process. You would have exactly the same thing. In imbibition, you have an inverted curve heading towards some residual oil rather than some remaining or residual water saturation. Other artifacts, the other main artifact when considering residual oil saturation is core flooding and the impact of capillary end effects on core flooding. So in a core flood, in order to get flow, you have to have some difference in force across the sample. If there was no difference in force across the sample, we get no flow. And so what we have to do is we either apply a constant injection. That constant injection will then create a differential pressure across the sample. So we have higher pressure at the inlet compared to the outlet. Or we apply a constant differential pressure or a constant higher pressure at one end, and that will cause flow to occur. And at some point we'll begin to get stable flow. So initially flow will be, you'll get a decrease, an increase and then a decrease in flow, a decrease and then an increase back in flow, and it will stabilize if we apply constant pressure. But what's happening is in this short plug, we have a differential pressure. We have half of the length of the plug, we'll have half of the pressure being applied. At this 3/4, we'll have a quarter of the pressure being applied in here, and until we get close to the outlet where we have almost zero or negligible differential pressure. What that's happening is it's setting up a saturation or a pressure gradient, a fluid gradient within our sample, and that will control saturation. Saturation is a function of the forces applied and the capillary forces holding against those displacement forces. And so what we have is we have a saturation gradient across the sample, a pressure gradient across the sample that will produce a saturation gradient across the sample. And these are actual measured data. So that line here is the solid line is the saturation gradient. But because relative permeability is a function of saturation, if we have changing saturation, we have changing, well, not relative permeability, because relative permeability, the curve itself is not changing. What's happening is if this is my saturation at one point of the sample, then this is my relative permeability at that point in the sample. But if my saturation is here, then my relative permeability is at this point. And relative permeability is really just another a dimensionless form of saying effective permeability. So what we're getting is a difference in effective permeability from one end of the sample to the other end of the sample, and it's a gradient. So the dotted lines in here are showing the gradient of that. So for different forces being applied, this is a low force being applied,
a low gradient, and this is the linear gradient in that core flood. What we see is this saturation gradient. This causes this gradient in my water curve, this gradient in my oil curve of relative permeability or effective permeability. And if I were to use a higher pressure, I would see this data. So slightly different saturation curve, saturation gradient, different water and oil gradients, and so on. So depending on how I perform the test, I could get different answers because of the impact of capillary pressure. So it's important that we understand the impact of capillary pressure, understand how that might produce incorrect curves, incorrect residuals. And so what we actually want to do is get to a correct relative permeability curve and a correct residual oil saturation. How do we do that? Well, simulation is one of those. So simulating those impacts, that means that for relative permeability, we need to understand the capillary pressure. We need to be able to history match our data and obtain and simulate out the relative permeability and a residual oil saturation, or we have to have some other way of determining residual oil saturation. So core flooding is actually the worst method. Usually, it's not always, but it's usually the worst method of determining residual saturations. So that earlier graph where I was showing the curve, the U-shaped curve of wettability, and the upturn at oil wetting in residuals, that's largely because it was done by core flooding without any consideration of correction for capillary end effects. That has the impact of suppressing recovery. It gives errors in the derived relative permeability and means that we don't always achieve the residual saturations. So what's the solution? Well, I mentioned earlier about how each of these processes control or have a potential impact on on the residual oil saturation. Well, we need to control those processes. We need to control coring. We need to control the trip to surface so that we're not damaging core. We need to control handling at surface so we're not damaging the core. We're not creating physical damage to the core. One ways of understanding and that we've done that is to look at CT images and determine that and see that the core has not been damaged. We then need to consider the cleaning processes that we're using and the different procedures we're using to ensure that we're using best practice procedures for those, and ensuring that we establish the correct water saturation that represents the water saturation in our reservoir, because that can have an impact on things like wettability. So if we don't have the correct saturation, our wettability may be incorrect. If we don't have the correct oil, our wettability may be incorrect. If we damage the clay system in our core, we may have incorrect wettability. All of that is going to produce incorrect residual saturations. And we need to ensure our stabilization criteria are good enough to make sure where we need to, we've achieved good, stable production volumes. So when we get our samples, we need to review the CT, look at features. All of these are ones that we are not really desirable for using in the sample, in a test. So we should discard samples with these sort of undesirable features. We need to remove fluid content. So if we've had precipitation of the reservoir fluids, we need to ensure that any precipitation is removed. We need to ensure that the clay morphology and minerals are kept have the same integrity that they had in the reservoir. And we need to obtain back to water wet if we're going to be using restored state processes. We then need to look at our rock properties, so porosity, permeability. We need to consider things like outliers. What's happening with those? Are they realistic? Are they just outliers and we need to discard them from further testing? So it's about thinking through all of these things, ensuring all of these are quality controlled and stabilized. And then we need to look at, well, what is currently the best method to determine true residual oil saturation? And I would suggest that at the moment, with the current practices and the current equipment that we have, then for most reservoir systems, and this won't be all, but for most systems, the best method will be centrifuge process. So a centrifuge test down to true residual oil saturation. That will require understanding bond number, and bond number is a term similar to capillary number in core flooding or in reservoir flooding, but for the forces applied in a centrifuge. So in flooding, we're looking at viscous forces versus the capillary force, which is basically permeability and interfacial tensions. In the centrifuge, we're looking at gravity forces against the capillary pressure and interfacial tension. So these are just some examples of some systems where residual oil was obtained, and some where even with the laboratory forces and the high forces were able to apply, it still was not achieved. So this one here is a native state set. So the samples were taken in controlled environment, brought to the laboratory, tested and made sure that there was no invasion from mud systems, and considered that we had the correct reservoir wetting. And what we see here is most of these samples are becoming asymptotic at the end. And they're becoming asymptotics generally around about 5 to 10 in remaining saturation or residual saturation. So this one does it by or achieves it in a bond number of 10 to the -7. These 10 to the -5, and this one about 10 to the -6. So there is a range, but we can see where stability occurs. So we've got reducing saturation down to this point, and we haven't gone into a further potential additional saturation reduction. This one sample here, which is not the most permeable and not the least permeable, but maybe had a different wetting than the other samples or some different aspect ratio. So it wasn't achieved in this sample. So these are showing you the permeability of these different samples. In this next one, so sister samples were taken. They were taken alongside those native state samples and went through a restored state procedure. And what we see is very similar residual oil saturation. So again, most of the residual oil saturation is 5 to 10%, but this sample again has not achieved it, and we've got up to 10 to the -5. So if anyone has ever read into Haggart's work and this limit of 10 to the -5, which is often portrayed in the industry, this has not achieved residual by 10 to the -5. And it's quite similar to the sample, its sister sample here in the native state. So here we can see a good consistency between native state and restored state, between the majority of the samples that have achieved residual saturation and this sample that hasn't. So this would still be some form of remaining. Here's another program, a different program, where two samples, so these are the tightest permeable samples, they have not achieved residual. And look at the bond numbers here, we're well above 10 to the -5. This sample here doesn't begin to achieve, or it doesn't even start. It's very permeable, and the smallest forces we're able to apply are pretty high in bond number terms already, and it doesn't achieve residual until 10 to the -4, but it's then very stable. Whereas these samples here, they are still not achieved true residual,
and we're above 10 to negative 5 and 10 to negative 4 in this particular case. Some other samples, another case where some were achieved and some not achieved. So all of these samples have achieved residual, but quite high residuals in this case, 30 to 35%. Whilst these samples here, and again, these are some of the lowest permeability samples. They have achieved it probably because they were water wet. Whilst these samples, which are more mixed wet, again, very high bond numbers, but still haven't yet to reach the true residual oil saturation. So residual oil saturation, it's important for the reservoir. It's important for your production calculations, for your simulations of production. It requires appropriate control of the processes. It requires representative core material, representative fluids. That may not always be the true reservoir fluids, but it must represent your reservoir under good representative conditions, and appropriate wettability is essential. And then it's vital to handle the core correctly, to ensure that you've got good procedures, a good selection process, and good quality control. So all of those aspects can affect our results. And a correctly controlled process, probably by centrifuge, is going to be the closest to true residual oil saturation. Still, that might not quite get us there. For certain samples and certain wettabilities and certain systems. But it's also be aware that any rel perms you will need to correct so that you're correcting for these capillary artifacts. Okay, thank you for your attention, and I think now we'll take some time and answer any questions that you may have. So there are 3 questions at the moment. Someone is, this is an anonymous attendee. Sorry, but can we estimate by past oil or bypassed oil a volumetric sweep efficiency from the lab? My understanding was that residual oil saturation is what would be the target of EOR. So there's a couple of questions in there. I'll start with the second one first, which is about residual oil saturation being the target of EOR. Well, what EOR has the potential of doing is reducing residual oil saturation even further. So you may be putting say a primary production process that's just going to be depletion of the current pressure. If you don't have an aquifer support, then there's going to be no real movement of saturation. It's just going to be under the compression of the system, production of fluid. Now, if you had aquifer support, or you go for a secondary process of water injection, then you're going to have changing saturation. So water ingress into the system and moving oil out. Now, in that process, you will have a residual oil. Now, what I'm saying through this webinar, through this presentation, is that in certain regions of your reservoir, because in the reservoir you don't have the boundary effects that we have in the laboratory. So certain areas of your reservoir will achieve that true residual oil saturation. They will get to very low saturations. If we see that in the laboratory, then we'll see those low saturations somewhere in your reservoir as well. If like that last, if I just go back a couple of, like this one here, probably if they were water wet, they've got high residuals. So that's going to be a high residual in the reservoir for these rock types as well, probably because of wetting. And if you remember that wetting curve, water wet tends to have high residuals. If people are putting questions into the chat, could you move them into the Q&A section? I can see things are happening in chat, but I can't see any questions that might be happening there. So that's one thing. So that's with residuals. The residual is set by what the fluid pairs that are present and the forces being applied around those fluid pairs. For EOR, we're bringing in something that's not native. We're bringing in either some other force mechanism or some other material to break down the interface between the fluids. And so we may even at 5 or 10%, but there's a question of whether you need to and what's actually added by getting lower than if your water flood was going to get to 5% in certain areas, what more additional are you going to get from an EOR, say a surfactant injection? But something like surfactant brings down the interfacial tension. And so we could get from 30% down to 0, ultimately, depending on the type of EOR being implemented. So there's those two questions in there. Residual oil saturation is only one of the targets of EOR. So EOR could reduce residual oil saturation even further than it would be normally, but you're also trying to improve sweep efficiency. And in the laboratory, we can't determine sweep efficiency from a plug. That's done by characterizing of the reservoir and understanding the different layers and the different properties of those different layers of your reservoir. So it usually comes from the geology and the routine core analysis and the petrophysics, determining the different layers and structure. Could I please comment on SWI versus SOR and the differences? So the differences here in SWI, so I probably touched on this a little when we discussed capillary pressure. So if anyone was present for my capillary pressure discussion, what we call SWI, and by that I'm talking irreducible water saturation, usually is not really irreducible. But if we're in a fully water-wet system, if our reservoir starts off as a water-wet system, we're bringing a non-wetting phase into there. Water is the wetting phase. We're bringing in, a non-wetting phase is injected into the system. That's separating out under gravity, and we're getting a fluid gradient which pushes into the smaller and smaller places. Now, if we had a very high column, if our reservoir is extremely thick, we would have higher fluid pressures, and so the fluid will push, well, the hydrocarbon could push into smaller and smaller capillaries. So theoretically, we could push into smaller and smaller capillaries down to 0 irreducible water saturation. So what we call irreducible water saturation is really only irreducible based on the reservoir properties and heights, the fluid properties, and any wettability that has been changed from the oil coming in and pushing water away, or is a limit in the forces that we can apply in the laboratory. In residual oil saturation, because water was already there and generally was the wetting phase, we then have a wetting change. SOR is a bit of a different, because it's no longer a percolation primary drainage process. We're now into an imbibition process where the water may still be wetting certain areas, and so you begin to have snap off of the oil column, which creates and if you remember those pictures of forecasts of residual oil, creates a droplet isolated all on its own. So that's really true residual oil saturation. That droplet is
is isolated. Any water coming through the system is just bypassing the oil, and no matter what you do, apart from some form of EOR, that droplet will remain constant in the middle of that pore space. So those are some of the differences why we, and this is theoretically again why I'm saying that that curvature against wettability is incorrect and unexpected, is that oil wet conditions, the term oil wet really means that the oil rather than the water is wetting the surface of the grains, and so the oil is now interconnected across the whole rock system. So then the residual oil there in that picture, just as I've mentioned about SW, in an oil wet case, the true residual oil is then just a function of the force being applied. But you get into different terms of whether you're in a drainage process, what your wettability is, or whether you're in an imbibition process, and what is the wetting fluid or the major wetting fluid. So those are all things that are controlling that process. Sorry, long answer for a short question. How would one estimate recoverable oil as a percentage of overall movable oil based on the Labco? So I actually provided the equation for that in an earlier, in one of the slides. So it was recovery factor is 1 minus SWI minus SOR divided by 1 minus SWI. Thanks a lot for the wonderful lecture. Is the oil fraction between the oil water contact and the free water level either connected or disconnected depending on wettability? So theoretically, there should be no oil between free water level and the oil water contact. So again, if we're considering a drainage curve, let me go back and see if I've got the drainage capillary pressure curves. Yeah, so it's maybe not the best because it's very small transition zone, so you can't actually see the entry pressure. But let's say that this wasn't zero, that zero was actually down here. What you have is this an area here that remains a water saturation of 1, and this would be entry pressure. And below this, you wouldn't expect any hydrocarbons. If you have that, so that's the oil water contact. And if this was a different curve where this was the real 0 point of capillary pressure, this here would be the free water level. So the point of 0 is the free water level. And then this, where this begins to reduce, is entry pressure. If you have oil below your oil water contact, but above your free water level, that would suggest you have a paleo contact. And what that means is that at some point, your reservoir has been lifted, or has been a fault pushing in and forcing portions of your reservoir that were below the oil water contact, now forcing them above the oil water contact, sorry, that were above the oil water contact, now forcing them below the oil water contact. So that you'll have some portions of your reservoir potentially that have been at some lower water saturation, had oil saturation present, and then dropped below, or it's been exposed as to the area of the inlet of the migrating hydrocarbon, wherever that may be. So that requires you go back, discuss with petrophysicists, discuss with the geologists about the reservoir history to find out what's actually going on there. But generally, any oil below the current oil water contact is usually from something like a paleo contact, or some influx of water to the system later, so that the oil there would be some form of remaining or residual oil saturation. Next question from Juan as well is, how accurate is the estimated oil saturation from water-based mud invasion? Can we say it's closer to the remaining oil saturation? So there, if you're taking a core, if you're thinking about the sponge core or pressure core, where you're using water-based mud, so there's no oil coming from the mud system, then any oil captured in, so the sponge core or pressure core is designed to capture any fluids. And if you find any oil present, that must be coming from the core. So what you have to do in those cases is you determine the saturation in the core. You also determine the saturation of oil in the fluids outside the core, in the sponge or the pressure barrel, and then make a correction for, because those would have been in the core, they've been pushed out as gas has expanded as you bring to surface. But generally they tend to be pretty accurate if everything has gone well. So Ruben says, great presentation, thanks. When achieving residual saturations in a centrifuge test, what's the best test technique to estimate centrifuge force necessary and achieve real residual? So what I was showing in some of these tests are what's called multi-speed centrifuge. So we're performing this purposefully at different forces, just as a continual process. So we wait for stability at this force, we then apply a larger force, and it's just continual increase of force until we get a stability, a bit like a porous plate process, but without the porous plate in place. So this is really like this is capillary pressure, imbibition capillary pressure, and we've got the stability there. So this is the one way. So you perform a multi-speed centrifuge test. That tells you here, well, we're basically at residual here. So whatever force that was using to apply for that sample, that's the force we need to apply to get residual saturation for that rock type. Likewise here, so here it's 10 to the -6, here it's maybe 5 to the -6, and here was less, but all of these samples here achieved by, say, 5 times 10 to the -6, so that's the force you want to be applying on any other samples if you're only doing it in one step. Adonai says, which practices would be best for handling and studying a core from a fractured gas reservoir? A centrifuge method would still be the most recommended. Well, yeah, so when you get into fractured reservoirs, you have to then consider, you know, what's actually happening from fracture to matrix processes, particularly in a gas reservoir. Generally, you're assuming that you're going to have strong water wetting, and that the matrix is going to produce into the fractures by spontaneous imbibition. So yeah, you need to understand the fracture system, but yes, for the residual gas, and then in this case, a centrifuge is not going to work for a gas system. So you either have to then think about a flooding system, and actually a strongly water wet case like a gas system is one of the times when the capillary end effects are have less impact on the residual saturation. That you could use core flooding for this. And centrifuge is not going to be good, because what the centrifuge will do with the gas for an imbibition is it will compress, during the testing, when you're applying a force, it will compress the gas into the center of the sample and appear as though you're having change. But as you stop the test, the gas will expand again, pushing the fluids out. So you get this disparity between what's happening when, and you could be just dissolving gas rather than displacing or moving gas. So a centrifuge is not recommended for those. Flooding is better. Alfonso says, oh, excuse me. Once again, exceptional talk. Oh, thank you. The question would be, is it possible to get a reference value for SOR with imbibition capillary pressure curves? And if yes, is it close to 0 PSI capillary pressure, or do we have to push below for when centrifuging? And this becomes a case of wettability again. So for water wet cases, something close to 0 capillary pressure will be approximately similar to SOR for very strongly water wet cases. As you get away from strongly water wet, and that, by strongly water wet, I'm talking on a wettability scale plus 0.5 and over. It's very strongly. As you begin to get lower wetting numbers, so positive 0.4, 0.3, 0.2, getting closer to 0, the more you come away from strongly water wet, the higher the force that you're going to need to apply in the imbibition process. So very often, for most liquid hydrocarbon reservoirs, you're going to need to apply some force in imbibition in a capillary pressure curve to get to true residuals. Good question, thank you. Laboratory experiments fall short of correctly predicting SOR for fractured reservoirs. And what's the best approach for dealing with fracture? Oh, so partly answered that already. And some of the issues around that, so just as a follow-on of what I was discussing about, you can't use centrifuge in this case. There is a lot of data on gas reservoirs and I wrote a paper, it was either 2013 or 2016, I can't remember now. But we were, myself and my co-authors looked at appropriate control of gas liquid systems, because a lot of potential errors come from lack of equilibration of the fluids. So that in many of the tests being performed, they are either dissolving gas or gases being evolved because of differences in pressures and because they're being performed under inappropriate pressure for those gas liquid systems. So they are more difficult to control than many laboratories consider, but you can put control in place and you can get good data. And so some of those might be spontaneous imbibition processes, and those tend to be quite cheap or relatively cheap. So you can do quite a lot of tests and get a good statistical variance of the residuals from those spontaneous imbibition processes. It's often called the countercurrent imbibition testing. Another one is connate water saturation the same as irreducible water saturation, and is that the same as initial water saturation? I think for most people in the industry, they're almost interchangeable. Connate, so I may have a different view on what these terms really mean compared to other people. So when discussing these terms, you really need to ask the person what they mean by the terminology they use, because different companies and different people will mean different things. But the word connate just means the water that is there. We might also call it innate or autochthonous. So those words basically mean what is there. So water saturation, if you're in the water leg, the connate water saturation might be 1. As you go through the transition zone, your connate water saturation, this is how I view connate, your connate water saturation could be reducing from 1 towards irreducible or towards initial. So it's reducing. So connate really just means the value that is there at that layer, at that depth of the reservoir, or that height above the free water level. Irreducible water saturation, how we refer that in the industry is generally just the smallest water saturation that's found in the laboratory, or sorry, found in the reservoir. So if you were to map or plot water saturation as a function of height above free water level, what you'll tend to see is that capillary pressure curve, where you see something like this, and as it begins to become asymptotic, so we begin to get what looks like a straight line, this we would call irreducible water saturation. Now, that only looks like a straight line because I'm plotting this from 0 to 90. If I were to plot this curve from 0 to 9,000, it would not look like a straight line, and it would look as though it's still curving. And if I were able to apply higher pressures than I'm showing here, it would begin to get down close to 0, except for any void space or disconnected pore systems. So the irreducible saturation, in my mind, a true irreducible, should be something close to 0. But what we mean in the industry, usually what is meant by irreducible is where the capillary curve is becoming asymptotic, or height above free water level in our reservoir is becoming asymptotic. By initial water saturation, that's often a laboratory term that roughly means the same as irreducible, but by laboratories who also may not like the term irreducible because it's not truly irreducible. If we had applied higher forces, we would have produced some more, which means it's not really irreducible. I hope that answers those questions. Okay. I was controlling my time during the talk. I wasn't controlling my time during the answers. Apologies for any going out a little over time here. I'll hand back to Jennifer now.
Great, thank you, Jules. Yeah, there was a lot of interesting questions there, so you managed to get through them all. We did have a few questions prior as well with the registration, so if there is anything that we didn't, or Jules didn't touch upon within the session, then we'll be sure to get back to you via email on those in the next few days. If you've got any further questions as well, just feel free to get in touch and Jules can look at them for you. You'll receive a link tomorrow with today's recording, so keep a lookout for that one in your emails. And if you've got a couple more minutes spare, I just wanted to do a quick poll here for you quickly. We normally have some set sessions that we plan for the next few months coming up, but we've decided today to leave it in your hands. And if you've got a quick second, if you want to pick your most preferred topic you would like to see next month, then feel free. Keep an eye out for all the info and registration links. They'll be up on the Premier Corex, LinkedIn and social pages over the next few weeks. If you give our page a quick follow as well while you're there, it means you won't miss any info or details or links for joining. You can, if you've missed any of our sessions, I know Jules referenced a couple of our sessions previously that we've put on. If you have missed any of them, they're all available on our Premier Corex YouTube channel, so you might want to have a quick check over there for some of those. I'll just give it one more minute for the poll and I'll end polling there. It's a bit different from this morning's winner. This morning we had Introduction to Core Flood Simulation, which won, but this afternoon everyone seems to be looking for relative permeability, core versus field. So I will have a chat with Jules and we will bring you one or the other next month, and then the other one the month after. So we'll be sure not to miss one out based on your choice there. So I think that's all from me. As Joe said, we have run slightly over, but thank you very much for hanging on. Thank you to Jules again. Thanks for attending, and we hope to see you at the next session. Thanks a lot.